Okay, welcome to today's Explainer. We're jumping right into a fascinating journey today, looking at how humanity and modern students learn to cross that massive cognitive gap between simple arithmetic and abstract algebra. Seriously, if you've ever stared at a math problem and thought, wait, why are there suddenly letters in my math? You are absolutely going to want to pay close attention. We're going to unpack a struggle that happens in classrooms every single day, and we'll trace its roots all the way back to the ancient world. So, let's start with a really common frustration. Why exactly do letters make math so utterly terrifying for middle schoolers? Well, here's the thing. The cognitive leap a 10-year-old is expected to make today actually mirrors a historical leap that the world's absolute greatest mathematicians struggled with over centuries. Think about it. We're asking preteens to suddenly think in an entirely new language, right when they're already dealing with the horrors of middle school. It's a lot. You can really see the stark contrast here. On one hand, you have the comforting certainty of calculating basic numbers. On the other hand, the anxiety-inducing abstract relationships of algebra. You see, early math curriculum is all about arithmetic, right? Manipulating real numbers to find a specific, concrete answer. But algebra is basically generalized arithmetic. The problem is that connection is rarely made clear in the classroom, so students end up seeing arithmetic and algebra as two completely disjointed subjects. Arithmetic is the straightforward path to an answer, while algebra just feels like this totally abstract, arbitrary set of rules.
Section 1. The Great Divide, the Arithmetic-Algebra Gap. Let's see how this plays out.
This disconnect, it builds into a massive modern educational crisis. Just 6.9%. That staggering number represents the mere fraction of 17-year-olds who scored at or above proficiency on multi-step problem solving and algebra in a 2005 national assessment. 6.9%. That is wildly low, and it highlights a huge systemic gap in conceptual understanding. When kids rely purely on memorizing rules rather than actually grasping the underlying concepts, well, things quickly fall apart the second the problems get complex.
So, where does this whole misunderstanding even begin? Usually, it's pretty early on, and it's because students fundamentally misunderstand the equal sign. Most treat it just as a command to output an answer, like it's a signal to do something, kind of like pressing enter on a calculator. But instead, they really need to see equations as a balanced scale. When students fail to see that an equal sign represents a state of perfect balance between two sides, the entire foundation of algebra just starts to crumble. Section 2. A History of Algebra. Let's take a look back in time. To really understand how to fix this cognitive gap, we have to travel back to the origins of algebra. Stemming from an incredibly influential 9th century treatise by the Persian mathematician al-Khwarizmi, we get the very word we use today. The Arabic term al-jabr roughly translates to restoration or completion, and this actually referred to the physical act of moving subtracted terms to the other side of an equation. Then you have muqabala, which refers to balancing or canceling like terms on opposite sides. You see, these weren't just abstract rules to memorize. They were physical, descriptive actions of literally restoring and balancing. And get this, it took humanity thousands of years to transition through these stages. We started with rhetorical algebra way back in 1900 BC in ancient Babylon and Egypt, where math problems were written out in literal full sentences. Imagine writing out the thing plus 1 equals 2. Wild, right? Then, around the 3rd century AD, a mathematician named Diophantus introduced syncopated algebra, which finally used some abbreviations. But actually, it wasn't until the 16th century, thousands of years later, that we achieved symbolic algebra with the modern variables like x and y that we use today. We literally expect preteens to grasp in a single semester what took all of humanity millennia to develop.
Section 3. Seeing the math, the geometric algebra connection. Long before those modern symbols were universally adopted, classical mathematicians proved that algebra is inherently visual. If we look at classical Greek mathematics, typified by brilliant minds like Euclid, we see a fascinating method called the application of areas. Instead of memorizing arbitrary algebraic rules, ancient Greeks used a geometric process. They would physically construct visual solutions to equations using lines and shapes, literally representing terms by the sides of geometric objects like squares and rectangles. When they needed to solve an equation, they drew it out. And modern interactive visual tools perfectly mirror this ancient geometric method. They work through this very specific 4-step rhythm.
First up, you have a starting square representing the left-hand side of the identity. Second, a labeling step to split the sides into named segments. Third, a physical dissection or rearrangement of the pieces. And finally, summing those pieces up to produce the right-hand side. The real magic here is that the total area is preserved while being physically reorganized to prove the algebraic identities. When these visual proofs come to life, it practically feels like magic. Take the square of a sum, a plus b squared. Visually, it splits a square right into a 2x2 grid of 4 rectangles, with the two AB pieces sitting perfectly at opposite corners. Or the square of a difference, a minus b squared. That one uses overlapping strips and a visible discard step, which makes that tricky negative middle term completely unmistakable. When you see formulas laid out as physical grids like this, the signs and coefficients stop being rote memorization. They're literally forced by the geometry you see right in front of you.
Section 4. Building the algebraic bridge. Let's bring this into the classroom.
So how do we bring this all back to the modern student? Well, educational organizations emphasize building this algebraic bridge systematically through 4 key components, and it starts early in elementary school. First, understanding variables and constants, making sure kids know that variables still follow the basic rules of arithmetic. Second, decomposing word problems algebraically. Third, lawful symbol manipulation. This means teaching that moving symbols simplifies the equation to maintain balance, not just to, find x. And fourth, grasping functions as clear input and output relationships.
Let's actually put this into practice with a classic scenario. Imagine Maria puts 6 identical boxes of cereal on one side of a scale. To balance it out, she puts 2 boxes and 3 4-pound blocks on the other side. Now, by identifying the unknown, the weight of a single cereal box, and translating it into a mathematical statement of 6y equals 2y plus 12, we do something totally vital. We reframe that equal sign as a balanced state, a literal physical scale, rather than just a simple command to calculate a number.
And the great news is, modern teaching is finally catching up with this geometric mindset. A recent RSIS international study successfully explored the lived experiences of grade 7 students using relatable, everyday scenarios, things like cupcake sharing or budgeting. By representing these concepts through physical bar models and colored strips, educators were able to reconnect those abstract, scary algebraic symbols right back to physical reality for these students. It's a total game changer for bridging that daunting gap.
Which brings us to a final, pretty profound question to end this explainer. If it took humanity thousands of years to transition from rhetorical sentences to visualizing and balancing the abstract rules of algebra, are we giving our students the right tools and, honestly, the right amount of time to build their own conceptual bridges? Ultimately, if you want to help every student achieve that incredible, satisfying aha moment, we absolutely must better honor the long, visual, and evolutionary struggle of mathematics itself. Thanks for joining me today, and keep questioning the math.